Hello everyone, bienvenue tout le monde à notre colloque, to our colloquium. May 12th is Mariam Rizakani's birthday and is Women in Math Day. And so this colloquium, our colloque des sciences mathématiques du Québec, is sort of officially our Women in Math Day event. And with that in mind, we are extremely happy to have our speaker today, Nilima Nigam, who's a professor at Fraser University. So let me tell you a little bit about her. She actually did her undergrad in physics and then switched to math, but not before getting 2 gold medals in the National Physics Olympiad. Was that in India or okay, in India? Then did a PhD in mathematics at the University of Delaware, a postdoc at Minnesota, and then was actually a professor here in Montreal at McGill from 2001 to 2008. So some of you may have known her from that time. I know at least one person, by the way, who wanted to be here today, but it just couldn't. And so was a professor at McGill 2001 until 2008, when she was stolen from Montreal by Fraser University, where she is a professor today. She also, among the many, I'm not going to sort of say everything that Nilima has done, but she's very accomplished. And one of the things that really stands out is that she was the Associate Scientific Director of MITACS, which is the Mathematics of Information Technology and Complex Systems organization, which organizes internships and other research programs that put mathematicians in partnership with industry. And so Nilima was part of the group that grew this program. It's huge. It's done something like 10,000 internships in the last 20 years across Canada. And so Nilima was instrumental in the growth of that organization. She's also, normally I say how many students people have had, but there was just dozens and dozens on her CV. So students and postdocs who speak very highly of her, as would I. Anyone who has a conversation with Nilima will be struck not just by the mathematics, but also her extreme wittiness and sense of humor. And then to say something about her research. So Nilima's research is in partial differential equations, PDEs, and numerical analysis on one hand, with a whole bunch of different scientific applications. So I've heard you and your students talk about applications in physiology, describing the movement of muscles, applications to electromagnetics and imaging, and then also on the theoretical side, spectral theory of operators, eigenvalue problems, and sort of connections to the numerics, and in terms of pure math, of reconstructing operators in terms of their eigenvalues. And so I hope that we will be hearing about some of these things today. So let's please give a very warm welcome to Nilima Nigam.
Thank you, everyone. It's delightful to be back. And I miss Jake, who was reciprocally stolen by Montreal from SFU. We miss you dearly. So it's a real pleasure to be here. And I thought about what to talk about today. And I picked this topic in particular because it's inspired by the work of somebody I admire greatly. And he gave one of the first talks on the so-called finite element exterior calculus here at the CRM more than 23 years ago. And it launched this huge field of beautiful mathematics. I'll tell you a little bit about it today. And I think some of what he spoke about here, he then gave a plenary at the ICM in. And I think it's a very nice bridge between traditional applied mathematics, computing, and quote unquote pure mathematics. So this is inspired by him and sort of an homage to him. His name is Doug Arnold, of the famous Doug Arnold, Ragnar Winter, and Rick Falk, finite element exterior calculus. All right, so this is work in part with a former PhD student, Joel Phillips, who got his PhD at McGill, and a current collaborator at Penn State, David Williams. And of course, this has stopped working. Okay, so I'm going to tell you very, very quickly about what a finite element is and tell you about what can go wrong. I think that's very interesting. Or to me, it's very interesting if somebody proposes a method to tell you what could go wrong, because that's where the interesting mathematical questions are motivated. And once I've spent a large amount of time on the beginning of this, I will then tell you how I will use the finite element exterior calculus to construct finite element pyramids. And then I'll tell you about some recent work I've been doing on finite elements in spacetime. So for those of you that aren't familiar with PDEs, a PDE or a partial differential equation, at its most abstract, is a functional relationship between some variables in space, x, y, z, however many, some unknown field u, which could be a scalar, or it could be a vectorial or a k form, and derivatives or differential forms of u. And these arise very naturally in all kinds of different physical and economic and sociological situations, or in biology. I've just grabbed some pictures from the internet. All of these are described by PDEs. And most generically, these are things that A, are very beautiful models we can write down, and B, lead to very interesting mathematical structures, and C, are usually intractable, right? So if I gave you this functional expression, and I asked you to solve it for you, generically, you're not able to write down a closed form expression for it. And so when people tell me that, oh, you're just computing, I use a response that I learned from Rustam, which is, if you think it's that easy, you do it. So what do? Well, instead of trying to solve the abstract problem, which, well, it's relating perhaps a function u that lives in some infinite dimensional function space x to some data or to some image point in another infinite dimensional vector space, I work on finite dimensional spaces. So I have some parameter h, which is destined to go to 0. I won't tell you what it is. It doesn't matter. But instead of trying to solve the very hard problem up here, which is in infinite dimensions, I'm going to solve a finite dimensional problem. And in the ideal world, the problem that I solve will have something to do with the original problem I would like to solve. Otherwise, what am I doing? So there has to be some sort of a relationship between these two things. And the numerical analysis of PDEs consists of defining these finite dimensional spaces in such a way that when I solve the finite dimensional problem, the solution converges to the true solution in some sense, as the parameters go to 0 in some sense. Now, what kinds of infinite dimensional function spaces will I be thinking about? We're agnostic. There's all kinds of function spaces one might think about. One might think of the so-called energy space H1. So we're thinking about scalar fields whose gradients are square integrable. In R3, we could be thinking about something called H curl. So these are vectorial fields whose curls are square integrable. And more generally, if I have a smooth and orientable Riemannian manifold, I could define function spaces of S forms. Okay, so here I would require that the exterior derivative applied to an S form is square integrable. And so here's the meta theorem. It's unfortunate that I can't get rid of the little bar on the bottom. The idea here is, if I have a numerical method that is consistent in the sense that the finite dimensional spaces and the finite dimensional operator L is somehow close to the true problem, and the method is stable, so the inverse of the operator at the discrete level here, if this is continuous, then as h goes to 0, the discrete solutions converge to the true solution. This is like a beautiful meta theorem in numerical analysis. And then we spend all our time designing consistent methods, trying to figure out that they're stable, and then we say, all right, we're done. Okay? So my favorite method for today is going to be the so-called finite element approach. And I need to tell you what that is. So a finite element mathematically is a triple. Okay? So I have some domain. It could be a triangle. It could be a little line segment. It could be a square. It could be a tetrahedron. It could be a pyramid. It could be this shape, whatever. On this shape, I define a collection, say, of polynomials of at most degree k. And then dual to this space of polynomials, I have a collection of linear functionals. These are called the degrees of freedom. So here's a very simple example. On this line segment T, I prescribe linear polynomials. And there's only really 2 degrees of freedom. A linear polynomial is characterized by its slope and its intercept. If I tell you both things, I've uniquely specified the linear. I could specify the linear precisely by telling you what the values are at the nodes. So that's a very nice finite element. Okay. And now what I'm going to do is if I have a longer interval, I'm going to take versions of that finite element and we'll put them together. Okay. So I'm going to take that original reference element, and then I'm going to make a copy of it over here, another copy over here, and so on. And I can glue these finite element functions together at the nodes so that I can enforce, for example, that things are continuous. Okay. So this is very useful because if I have a really large domain, I can tessellate it. I can tessellate it with copies of the shape that I chose in the beginning. And then I use the polynomials that I had on that simple shape. I glue them together in some nice way. And then I have a way of describing functions on the whole wide domain. And here is one such function. Now, of course, how I glue things between elements. So for example, how I glue a linear polynomial from this side and this side is going to determine the properties of the overall functions I can approximate, right? Notice that here I'm insisting that the value at this point matches from the left and the right. So I'm enforcing continuity. I don't have to. So here's a little example. I'm trying to approximate a Gaussian bump on a disk. Okay. I've taken the disk and I've tessellated it using these triangles. It's a terrible approximation to a disk, but bear with me. Okay. I've got a bunch of triangles here, and on each triangle, I'm going to take a linear approximation to a Gaussian bump. Now, if I insist that they're continuous across the edge, this is what I get. It's not great, but it's not terrible either. It's not really a Gaussian bump, but it's not terrible. If I didn't enforce continuity and I let things sort of match only at midpoints of triangles, I would get this approximation. This is discontinuous. This function is discontinuous as an approximation to the Gaussian bump. It's allowed, but I don't like it. This is what I would get if I, instead of taking linear polynomials on a triangle, I took quadratic polynomials. So I have more degrees of freedom, I can do a better job. So even though I only have a few triangles, I do a much better job of approximating a Gaussian bump. I could also go the other direction. I could just take more and more triangles. And if I did that, using even linear polynomials, I'd do a pretty good job of approximating the bump. Okay. And even if I allow things to jump across the edge, if I take enough polynomials, I can't see the difference. So I thought I'd walk you through the 1D problem. This is my favorite elliptic PDE. It's not even a PDE. It's a very nice example of what can go wrong. Okay? So I'm trying to find a function u on the interval -1 to 1, which satisfies a second order ODE. Here c is a constant, fixed, non-zero, okay? Positive. I insist that on the endpoints, the value of u is 0. Now, I could solve this problem. It's a second order ODE. I could do that. But I'm going to show you how I would use the finite element method. So I take this problem, and I can show that a solution of this problem will necessarily be a minimizer of this function. So this function right here is very nice because now I suddenly don't need to have 2 derivatives I can actually just make sense of this even if my first derivative were only square integrable. So a solution of the problem in blue is definitely a solution of the problem in red. But the problems in red need not be solutions of problems up there. This gives me a much richer space to look for solutions in. And it turns out that solving this problem is equivalent to solving this problem at the bottom. Okay? And this problem at the bottom is what we will solve using a finite element method. So solutions of this are solutions of this and vice versa. So what's the finite element method? I write down the weak form of the problem, and then I just put h's everywhere. Very nice. So I've got a finite dimensional subspace of the space I'm looking in, and I seek a discrete solution in there so that for any test function vh that I pick, I satisfy this expression right here. Now, this problem is suddenly finite dimensional. So what am I going to do? I'm going to use precisely elements like these and a finite element space constructed from it to solve this problem. Okay. I'm going to look amongst all possible functions that are piecewise linear, that have this form, that satisfy this expression, this weak formulation. And if you look on the left, you can't really tell apart the true and the computed solution. It's a really good approximation. Okay. And just because I wanted to, on the right, I'm plotting in blue the first derivative of the true solution, and in green, the computed derivatives. So I've got a discrete solution, I can compute the derivatives. And you can see that, yeah, the computed solution has piecewise constant slopes, as expected. So that's nice. But now I can get ambitious. I go back to the problem I'm trying to solve, and then I introduce an auxiliary variable. So I'm going to introduce a variable s, which is c times the derivative of u. And then the problem I'm trying to solve asks me to find a pair, s and u, so that minus s prime is equal to f. It turns out that the variational formulation for this problem is a saddle point problem. I no longer have to find the minimizer, I find the critical point or the saddle solution of this functional right here. So my t variable has to be in h1, and my v variable has to be square integrable. The corresponding weak formulation is a pair of equations, which are written down here in blue. And formally, this is, it's not bad, it's the same thing. But now that I have two different equations in my weak formulation, and I have two different objects, s sub h and u sub h, that I'm searching for, I have choices to make about the finite element spaces they go in, right? So one choice is the auxiliary variable is going to consist of piecewise linears, and the variable u is going to consist of piecewise constants. We do that. Why not? Another choice I could make is to take piecewise quadratics for the auxiliary variable and piecewise constants for the other one. Well, here's what happens. True solution is again in blue. Okay. If I use the first choice of finite elements, then I compute this object in green, which is not a terrible approximation to the blue curve. However, if I used the second choice, what I compute is this curve in red, which is completely wrong. Okay? And the problem becomes even more sort of striking if you look at the auxiliary variable. So the auxiliary variable here is in blue. The computed auxiliary variable is in green. That's a great fix. However, if I use the second choice, the second pair of finite elements, what I get is this stuff in red, which is complete garbage. Okay, so the point here is, even for a very simple problem, an ODE that I could assign to my students in their ODE class, and they will hate me, it is possible to do numerically some terrible stuff. Okay? So the issue was, when I picked my choices of finite element spaces, I wasn't careful. I picked an unstable pair. And what that means is, I can stare at the saddle point problem I was trying to solve. I failed to satisfy two conditions. These are called the Babushka-Retzi-Lattanskaya conditions. These sort of stipulate how pairs of finite element spaces have to talk to each other. Okay? I can't just pick them willy-nilly. If I've got a pair of finite elements floating around, they need to fit together just so. And if they don't, instability occurs and then I don't converge. So I'm not going to go through the details of what these conditions are. For the finite element people, the old finite element people in the crowd, you know what these are. Suffice it to say, this is a fitting condition. And it's not just bad, it's very, very bad. So if I tried to solve an eigenvalue problem for this very simple expression, the second derivative equals minus lambda u with zero boundary conditions, I know what the exact eigenvalues are. I could try and solve this using finite elements. And if I pick the wrong ones, what I will converge to very convincingly is 6 times the correct eigenvalues. So here are the exact ones. The exact eigenvalues are 1, 4, 9, and so forth. As you increase the number of subintervals you have, you should be converging to something. Read a row over here. So when n is 8, I'm at 5.7. When I double the number of intervals, I'm at 5.9. If I keep going, I'm converging to 6, not 1. Now, the only reason you know this is garbage is because you have the first column over here. If you didn't have the first column, you're solving an eigenvalue problem, you look like you're converging to something. It's the completely wrong spectrum, right? So this is your first, I guess, little diagram. So on the very top, we have the simplest differential complex I can think of on R. D is a derivative. It's the exterior derivative, it's the first derivative, whatever you like to call it in one dimension. Associated to it, there's a Hilbert complex, which takes my energy space H1 using the same derivative into L2. I constructed a finite element space which approximated H1. I constructed a different one to approximate L2. So there's a relationship between the two things. What I neglected to check was whether I have an arrow in the middle and whether the diagram commutes. Okay. So it turns out, it's a beautiful mathematical fact that in this field of numerical analysis, like in many other fields of mathematics, if you have diagrams, you'd like them to commute. Okay. We would like this diagram to commute. We would like to build our spaces S and P so that if you go from the full space to the discrete space and then take a derivative, it's the same as going from the full space, taking a derivative, and then coming back to the discrete space. Okay. If you have such a diagram, if these two spaces fit together just so, you have a stable pair. Yeah.
The bottom arrow should be a discrete derivative.
Yes, it is a discrete derivative.
It's not the same D.
It's not the same D, it's the differential D. So you might think this is much to do about nothing. because, well, the problem arose because I was working with two finite element spaces and they didn't fit together. So maybe I could avoid that problem. Turns out you can't. So here's an example where I've got a PDE on this L-shaped domain. The true solution looks like this. I'm looking for vector fields U that satisfy the PDE and some boundary conditions. And this is what the vector fields are doing. Okay. They have very singular behavior near the reentrant corner. Now, if I did a completely boneheaded finite element approach, what I will compute is this, which is completely wrong. Okay. You have to compute the solutions of this problem using a mixed method. You have no choice, and this is the correct solution. Okay. So here, what fails is consistency. So we led somehow to these complexes or co-chain complexes. So again, for an orientable Riemannian manifold, you have this very nice property that if you take the zero forms, then the exterior derivatives put you with the one forms. You take another exterior derivative, you get two forms and so forth. In 2 dimensions, you have two possible identifications of the exterior derivative. One is through a gradient. You get one complex. A co-chain to that would be if you use the curl of the exterior derivative. In 3 dimensions, here's the familiar deRham sequence. So the exterior derivatives are grad, curl, this. And this is where the finite element exterior calculus comes in. The idea is, if you're given a smooth Riemannian manifold, we can build finite dimensional spaces which approximate the Hilbert complex and satisfy this commuting diagram property. Okay. So up here you have the Hilbert complex, which goes with the complex above. At the bottom, you've got the discrete complex, and each of these boxes computes, which is lovely.
Actually, 8 is like that, where they do the discrete approximations converge continuous for differential forms and so on. But I think they were doing for the
I'm not familiar with the work.
But the interesting.
Yeah, I'm not familiar with the work. So it's possible. I'm not familiar with the work. What I do know is that Whitney came up with a collection of discrete spaces. He was not thinking about finite elements. And the Whitney forms go back to 1957. And then the connection to finite elements was discovered in 1988 by Bossagut. The point I want to hammer home, and the only thing to take away from this talk, is that if you want to get good approximations of solutions to PDEs or eigenvalue problems, you must preserve structure. This is non-negotiable. Here's another example. I'm trying to compute here the eigenvalues of the electromagnetic resonator, or the Maxwell eigenvalues. Here is a tessellation of the domain. My domain is going to be a square. Say, if I use the wrong finite elements, I get eigenvalues that look like this. And these are all garbage. The true eigenvalues are sums of squares of integers. These are the true eigenvalues. And to get these, I have to use the correct finite elements. I must not use WH. WH approximates H1. The objects I'm looking for are one forms. I need to use approximations that are discrete one forms. So there's a whole zoo of finite elements. So in 1 and 2D, here's a sample reference element. If I prescribe values at 2 ends, I get piecewise linears. If I prescribe them with 3 points, I get quadratics and so on. I can take the approximants of the next space over, so the one forms, they will just have this structure. In 2 dimensions on simplices, I have this collection of finite elements. And it turns out, because I have 2 possible choices of exterior derivatives, over here, I could pick either this finite element or this one, depending on which choice of exterior derivative I made. These are called edge finite elements. These are the usual Rabiot-Tomar elements. In 3 dimensions, again, you can have a whole family of different finite elements. There's in fact a periodic table of finite elements, which is very nice. You could have higher dimensional versions of these. You could have higher order versions of these. So like I was saying, in 3 dimensions, if you had a tetrahedral element, you could specify the values of the nodes. That gives you piecewise linear approximates of H1. If you specified the values of the tangential components of vector fields, you get the lowest order approximation of H curl and so forth. You could have higher order polynomials. So this is the degrees of freedom here. I specify the values at the nodes and the midpoints, or I specify 2 components of the tangential trace and so forth. There's a recipe for this. So if you're sitting on a simplex, there's a very nice way to write down what the finite elements are, at least abstractly. This is taken from the beautiful paper by Arnold, Falk, and Winter. This is the prescription right here. It's impossible to stare at this and think, oh yeah, I can code this up. So, it's a very beautiful query, very elegant. And for a long time, the engineers were not using it just because getting into it took a little time. Implementing it takes a lot of time because you really have to get into the details. I can write this down very elegantly, but when I start to code this up, I need something explicit. So that's one challenge, how to make this explicit. The second challenge is, this is a prescription on simplices. What if you don't have a simplex? What if you have a cube? A cube is not a simplex. What if you have a pyramid? In fact, you could have a pyramid. You could have a prism. This is not a simplex. You could have a brick that's deformed. This is not a simplex. So I would like to define finite elements in all of those things. And I would like them to have the commuting diagram properties. Can I do this? Well, this challenge I set myself was, while I was in Montreal, was to build finite elements on a pyramid. Why? Seems like a crazy idea. It was known to be one of the big hard problems in numerical analysis. How do you design high order approximation for 0, 1, 2, and 3 forms on pyramids? And this came about because of engineering needs. So when you are building these finite element approximations in very complex shapes, sometimes you've got a tessellation that has tetrahedra in part of the domain and cubes in other parts. But you've got to chop or glue these together. You've got to go between tetrahedra and cubes, and the only way to do it is to stick a pyramid in there, like these shapes. But if you don't have finite elements on the pyramids, then what are you doing? So we decided we were going to solve this problem, and the goals were, well, we had to make sure that we could describe degrees of freedom. We had to make sure that whatever I did on the pyramid, the stuff on the faces, the edges, and the vertices was compatible with things from the neighbors. So pyramids have to talk to tetrahedra. Pyramids have to talk to cubes through their faces and edges. We insisted that the commuting diagram property held. This is non-negotiable. And we wanted our finite element spaces to contain high enough polynomial degrees so that we were approximating well. Turns out this is a really hard problem. And here's an explanation why. There's actually a negative result. There is no high order finite element on a pyramid whose approximation space consists only of polynomials and whose values on the polynomials. Here's the counterexample. Consider this function right here. This is clearly not a polynomial. If I examine this function on the faces of the pyramid, what I get is, well, exactly polynomials. So I've got this function sitting in my H1 space, which is not a polynomial, but if I look on the sides of the pyramid, it looks like a polynomial. So there's absolutely no way for me to achieve high order approximation without including things like this.
Is the non-polynomial function have holes in the middle of the pyramid, or is it like
Very, and that's okay. This versions of this negative result. So one is that it's impossible to construct these pyramidal conforming elements using only polynomials. There's no global equivalent onto element-wise polynomials. The projector cannot be bounded. And as a result, progress on this stalls about 30 years. So the very first approximates of H curl first and second degree were 1999. Then it's working again in 1999. Then finite element spaces, but only first order. It first came out in 2007, and then we refined things. It wasn't until that work that we built a higher order approximation space. I'll go through the details. I'll tell you what we did. That was kind of crazy. This is a reference pyramid. This is the object on which I want to describe the finite-dimensional function space. This is very hard to work with. So what we did was we said, instead of working with this, we're going to work with an infinite pyramid. We're going to take what we done took right there, and we're going to take it to infinity. We're going to map it to infinity. And we're going to work on this shape right here. This is very symmetric. Functions to decay simply fast to infinity. Once I construct things over here, I can just pull them back properly. And that's it. I mean, I can't tell you how many beers it took to come up with this idea. Resolution of singularity. This is actually embracing the singularity. The standard practice, if you're given a pyramid like this, is it's resolve a singularity by mapping to a cube, but a finite dimensional cube. That's the Duffy transform. That doesn't work. That really did not work. That's why we have to drink our beer and take it out to infinity. What kind of beer? Oh, so well, it's beautiful. I'll first tell you what the spaces are, and I'll tell you exactly the approximation again. So on the infinite pyramid, in each direction, we take tensorial polynomials. So polynomials of up to degree k in the x and y direction. They're weighted by 1 plus z to the power k. That's so that they have the correct decay behavior. When you map them back, you will get a collection of spaces which have rational polynomials, all polynomials up to degree k. So you will have approximation measurement. My rational polynomial space is rich enough to contain the suitable polynomial with high enough degree. And that's what you need. So here, the exterior derivatives on the spaces we constructed are well defined. They are, in fact, they form an exact sequence. They conform. So the spaces we construct are exactly approximating the correct infinite dimensional space. Here's the polynomial approximation. Here you have enough polynomials inside your discrete spaces. The top of the neighbors, so the period talks to the tetrahedron and to the cube. And beautifully enough, also satisfy the commuting diagram property. So this was great. We were so happy when this happened. And then I gave up this business for many years. I thought, oh, beautiful. Got it coded up. It's part of the production code with Lano. It's lovely. I'm happy. Made my mark. Somebody came to me and said, what about space time? What about 4 dimensions? Like, well, why? Here are maximum equations. I love maximum equations. Okay. You can think about them in terms of vector fields that are time dependent. Think about this well. We've got these vector fields and they change in time. And so for each fixed time, I'm going to create a one with the electric field or the ground. I could this is well known. And then since Einstein knows this from way back in 1981. So he knows that it is as either the one forms or the other forms sitting in our tree. Observer independent of distance. It's worse than that. If you think about the momentum that satisfies this expression here, the value of momentum depends on which observer you've got. If they're in relative motion, so you've got the same physics, and they're telling you the different momentum for the same physical problem. That's not allowed. So the way to resolve this is to work in 4 dimensions, but carefully. It's extensive work. It's just the recipe I showed you. It's beautiful. This is not many high order explicit constructions in R4. If you've got space and you want to do finite elements on there, and you want finite elements for all the forms, so the first instruction, the instruction in R4 that I know is only in 20. And that's the first time that somebody wrote down all the finite elements for the 0, 1, 2, 3, and 4 forms. So was used in 2018. We decided to use a different complex. So our definitions of the exterior derivatives are different. Just to get a feel for these objects are the 0 forms, think about them as scalars. The 1 forms are like 4 vectors. The 2 forms are like symmetric matrices. So here's what the derivative is outside. I don't expect for R, the deRham computation. It has to be associated with the complex. There's a next to this, which is what you need if you want to do integration with parts. Why this choice? Why did I choose the sequence in red and not the sequence in blue? Well, because of Maxwell's equations. They fit naturally into our system. So here's how we do this. We define two forms, the so-called Maxwell two forms that conform contains forms of energy. So it's a skew-symmetric matrix with these components arranged in a skew-symmetric form. Associated with this is something called a Faraday equation. Take the charge of the form, put that into a two form, and then ultimately you get a very description of Maxwell equations. So in the form, the curl, Maxwell gives you the data, the curl, the zero, divergence of the data too. So the similarity is the boundary traces of objects are. So for 0, 1, 2, and 3 forms, you can write them down. Here's what the integration by parts might look like. You do have to combine derivatives from both the discrete sequence or from the differential complex and the codifferentials. This is sort of hard-coded. We had to actually figure out what the traces were. Nobody had written them down for us. So I'm going to show you very quickly what to do if your finite element needs to be built on a tesseract. A tesseract is something from the Marvel movies. It's also a 4-cube. So here are the spaces that we get. We get tensorial products of polynomials for our first space. Then we get, think about vectors, and their first component has k minus 1 degree polynomials in the x direction, k, and k in the y, z, and w directions, and so forth. So we can explicitly characterize what these functions are. They satisfy a discrete sequence. We can specify the degrees of freedom. Nobody's going to remember this, but this is, for example, how we define some of the degrees of freedom in the middle. And most importantly, we've built them so that they satisfy. So this is, as far as I know, one of the first fully explicit constructions of finite elements in 4 dimensions of high order on the tesseract. We've also written down in explicit form the high order families on the simplices and on the prisms. And here are some references. All of our work is motivated by the finite element exterior calculus, this principle that if you have a whole bunch of function spaces that fit together in a differential complex, their discretizations have to do the same. And so for future work, while I'm thinking about degenerate elements in R4, and most recently high order families for the Lorentzian manifolds, which are just a complete there. So that's it from me. Thank you very much.
Question for a speaker.
Thank you very much for the great talk. So this idea of commuting diagrams that you illustrated in the case of finite elements, can it be applied, say, to spectral methods and other methods?
Yeah, there's nothing sacred about the discrete spaces, right? So in principle, as long as you have a finite dimensional collection of spaces that form a sequence, and you have interpolants that take you from the Hilbert complex to the discrete spaces, you want to make sure that those things commute.
It's something that people have actually studied, like in Colloque spectral method?
I think so.
Okay, cool.
I have a question about where you told about Maxwell's equations. So I didn't understand part of it, which was you said that the formulation of Maxwell's equations made these quantities seem
Observer dependent?
Yeah,
Yeah.
observer dependent. But how is that related to the question of writing down finite element methods to approximate solutions?
Excellent question.
Like a theoretical problem.
So it's interesting. So you might, if you're starting to simulate electric fields and magnetic fields, you could say, I'm going to think about this as a collection of fields that march in time. Okay. So I will discretize in space using a finite element. And then I will have changed the problem in space to something that's a finite dimensional problem in space, still left with a time variable. So now I'm going to march in time, but I'm thinking about a dynamical system. So time is now a distinguished variable, but that doesn't really work because of the stuff that I described. And so especially if you're working with relativistic electromagnetic fields, so when you're really thinking about space and time sort of not being independent, somehow space-time is one manifold in R4 with this property that can't move faster than the speed of light, suddenly you can't really disentangle time from what's going on in space. So when we march, or when we want to evolve our electric and magnetic fields, we have to do it in a way that links what we're doing in time with what happens in space in a smart way.
The follow-up question then about the shapes of the finite elements, then is there some kind of idea that if you have time as a distinguished element, you're doing something like a finite a prism shaped
Yes,
finite element?
that's
and
exactly
instead
correct.
You want it to be somewhat symmetric, like a
A
tetrahedron?
simplex.
Yeah.
A simplex in R4.
I don't think this doesn't make sense, but is there a way of making the commutative diagram connecting it with Bushka stability condition if and only is?
Yes, I think you can in fact make this an if and only if thing. Yeah, yeah. In fact, you got this guy sitting right next to you who's the boss man of all of this. Jason.
Yeah, I have another question. Coming at this from the algebraic geometry perspective, when people mention any kind of polytope to me, I tend to think of like toric varieties and families of polytopes. And so cubes and simplices are kind of special because the base of a simplex is the smallest simplex.
Right.
Are there any other I guess that's why those were the first two families you mentioned, but
Yes.
are there any other like special classes of polytopes that are particular, like you mentioned I forget what the different pyramids and prisms and texts or something.
Yeah,
like that,
yeah,
but
yeah.
What was that coming from?
Okay,
Why are those
so
things important?
excellent question. So simplices are special because of precisely the reason you described. If you take a facet of a simplex, it's still a simplex. Cubes are also special because everything cube in a facet is still a cube. If you want to glue those things together, that's one of the kinds of objects that will be of interest. So if you try to glue together a simplex in R4 with a cube in R4, you will be led to something called a cubic pyramid, which I think looks like this guy. Right? This is a depiction of it. And another degenerate object that arises in these composite meshes would be the bipentatope. I think that's what it's called.
The what?
The bipentatope. So this is another degenerate element. But these are the only two that I know of in R4 that arise sort of naturally in a composite mesh. There may be others. This one, yeah, they're both proving to be a bear because again, there's a negative theorem we just proved showing we can't generate high order finite elements of this using only polynomials. This one as well, but the class of objects you have to include here is much weirder. So still work in progress.
Just in part of that, so in fluid dynamics, people look at vector fields which are like eigenfields of
right?
Kind of steady solutions to over
Yep.
And so using this, you can, of course, you should be able to get like on a 3D box on the torus periodic conditions all the ground state of these things. There are ABC flows.
What should be able to, yeah. Solving these eigenvalue problems in 3D especially, not a problem. Come to my talk on Monday.
But on the sphere, the ground state comes from, I think, the bulk vibration.
Right.
And these days are in plasma physics, they're useful.
You can use finite elements to try and approximate the eigenstates in spheroidal or toroidal or
whatever shape geometries you would like. Yeah,
And this was good for nonlinear equations.
well, so not what a can of worms. So for a nonlinear PDE, one strategy is one performs a sort of nonlinear solve or nonlinear iteration. Think back to Newton's method. Okay, so what we're going to do is we're going to make a guess, and then we're going to try and refine our guess, and we're going to do it like Newton's method. But if we're doing that for a PDE, every step of the Newton method is now a linear PDE to solve, and that's what we do. So that's one approach.
Okay, let's thank our speaker again. There's a section just over in the other room, so please come and have some food and wine and meet our speaker and everything.